Hello, we're Team Hexagon. Our project is part identification and post-processing using a collaborative robot. Our technical directors are Jonathan O'Hare and Dr. Soli. I'm Lon, an electrical engineering student at the University of Rhode Island, and joining me here today is my project partner, Luke Watkins, majoring in computer engineering. Hexagon is a company located in North Kingston, Rhode Island, the world leader in quality control solutions for manufacturing, and they provide specialized hardware and software services for quantum measuring machines and other manufacturing products. The scope of this project is to create an automated inspection system. There are three key components for this system: a cabinet with drawers at various heights, which is shown on the left side of this picture, and in between the cabinet and quantum measuring machine is our Cobot. The role of Cobot in this system is to transfer the parts from the cabinet to the quantum measuring machine for it to measure the precise coordinates of the parts. But before the robot can perform its tasks, the parts must be manually loaded into jars, and the information for each part will need to be manually entered as well. This method will not only create additional labor costs for the company, but is also prone to human error. The lack of automation for this system is what motivates us to achieve these three no objectives. There are no human intervention, no single object data entry, and no human error. The best anticipated outcome for our project is to create a robust, reliable, and user-friendly object recognition system, with both hardware and software systems combined to achieve these goals. Our design involves multiple cameras located above each jar to obtain a full view of the jar and process the image data using our algorithm to detect the presence of the parts, and eventually use our trained neural network model to recognize the parts. We're happy to say that we have achieved our best anticipated outcome, and the implementation of our design will best mitigate errors caused by human operators, improve the efficiency and traceability of the system, optimize inspection process, and reduce labor costs, and eventually making the entire inspection process fully automated. On the hardware side, we spent a lot of time doing research during the beginning and selecting appropriate components to include in our design. We ended up using Raspberry Pi and Raspberry Pi cameras along with magnetic switch sensors to build a separate system that would not interfere with the robot. The magnetic switch sensors will be installed underneath each jar, so when a jar is opened, our program will collect the data from the sensor, which indicates the location of the open jar, and send a signal to activate Raspberry Pi cameras. The cameras are mounted above the cabinet on the opposite corners so they can have a full view of each jar despite the height differences. Once the camera receives the signal, they will then start identifying parts, and if any motion is being detected within the frame, the camera will store this process as clips for operators' reference. With this system, we can determine which jar is being opened for inspection, capture potential errors, and document the process for future references. And now Luke will explain in detail how we have enabled our system to recognize different parts.
The following block diagram shows how the software is intended to function in the process of obtaining an image from the Raspberry Pi camera and detecting and classifying all of the objects present within that image. The process begins using the obtained image as well as optionally a second image of an empty drawer that serves as a background mask. These images are passed through a script that performs background segmentation and object detection on it, determining the position of and number of objects present in the drawer. The object information is then classified to determine which part it is, and then this information is combined by the final output formatting script to create a JSON file describing the location of and type of each part in a format that is recognizable by the Cobot. The first step in this process after obtaining an image is the background segmentation. As I stated previously, this script performs this action, takes as input the current image of the drawer as well as optionally an image of the empty drawer. If both images are inputted, the background segmentation is performed by using the second image as a background mask and classifying pixels based on the difference in Euclidean distance between the same pixel in the two images. Likewise, if only one image is inputted, the background segmentation is performed by using phase congruency thresholding. Both methods return a bit mask with the same dimensions as the input image, identifying the foreground and the background of the image. After testing multiple methods of performing background segmentation, we selected phase congruency thresholding because it was the most consistent in correctly identifying objects in the image. This method consists of 4 steps: calculating combining orientation images, denoising output, applying hysteresis thresholding, and finally filling in holes. The first 3 steps perform the function of identifying edges present in the image, while the last uses that edge information and combines these edges to generate object boundaries. An example of this process working on multiple images can be seen in the GIF on the right, where each frame of the top animation has had this process performed. After the 3rd step, the result is what is shown in the middle image, and then the final result is shown on the bottom. Another key accomplishment deals with the next step of the process, using the background mask to segment individual objects and identify object boundaries. Given the bit mask from the previous step, as well as the original image, our project is able to determine the number of objects present in the image, as well as their locations. Using this information, the script creates an image of each object cropped around its center of a specific resolution to be inputted into the object classification. The next step in the process is to use the convolutional neural network trained by our interdisciplinary teammates to classify each object using the single object images. This model returns the information on the object type, a bounding box around the object, giving its location in the image, as well as the confidence factor of the prediction and classification. Using these classification predictions, as well as information on the drawer number and position of each object, the final script calculates the offset of each object in a drawer grid and generates a JSON file describing each object for the Cobot so that it can be retrieved and measured. We'd like to thank everyone that's helped us with this project.